Imagine you are analyzing a collection of legal briefs. The word "the" might appear thousands of times across every document. Does it tell you what any single document is actually about? Not at all. But what if the word "patent" appears 50 times inside one specific document, while barely showing up anywhere else? Instantly, you know that document's unique signature. This is the core intuition behind TF-IDF. Term frequency, or TF, measures local volume. How often does a word appear inside a single document? The more a word occurs locally, the more important it seems, but local frequency alone is lying to you. It gets drowned out by generic traffic words like and, is, and of. To fix this, we introduce inverse document frequency, or IDF. IDF acts as a global scale of rarity. It looks across your entire database and penalizes words that are everywhere, while massively boosting words that are rare and distinct. By multiplying term frequency by inverse document frequency, we form a perfectly balanced mathematical engine. TF-IDF acts as an information filter. It extracts the exact terms that are highly concentrated locally, yet unique globally, allowing computers to instantly map the core topic of any text block. Let's translate this visual intuition into mathematical truth. The TF-IDF score is computed by evaluating its two underlying formulas sequentially. Term frequency can be expressed in its simplest form as the count of a specific term, T, inside a document, D, divided by the total number of words in that same document. This normalizes long documents so they don't unfairly manipulate the system. Next, we calculate inverse document frequency. Here, we divide the total number of documents in our entire collection, capital N, by the number of documents containing our specific target word. But if we stop here, a large document database creates numbers that explode too quickly. To compress this scaling curve, we wrap the entire division inside a logarithmic function. When we multiply these two numbers together, something beautiful happens. If a word appears frequently inside a document, its TF component pushes the total score up. But if that same word is scattered across every document in your database, the denominator inside the log function grows, forcing the IDF component down to 0. The final output is an explicit score of distinct informational value. Algorithms can't read words. They read geometric coordinates. To feed text into a machine learning model, we must map our calculated scores into a document term matrix. Imagine a structured grid. Each row represents an individual document in your collection, and each column represents a unique token from your entire global vocabulary database. If you have 10,000 documents and 50,000 unique words, you get a massive high-dimensional math grid. Initially, this grid is just filled with simple raw word counts. It's an unweighted, primitive map. But watch what happens when we pass this raw landscape through our TF-IDF engine. Generic vocabulary columns collapse entirely down towards 0. Meanwhile, highly specific keywords flare up into distinct, high-value floating point weights. Every single document has now been transformed from a string of characters into a precise mathematical vector coordinate in high-dimensional space. Documents with similar topics will now naturally cluster near each other, giving models a clear mathematical blueprint of structural similarity. Once text is mapped onto a document term matrix, an invisible trap emerges: the problem of document length skewing. If you compare raw TF-IDF coordinates using standard Euclidean distance, long documents completely break your retrieval model. Consider a concise two-sentence patent abstract. and a comprehensive 30-page legal brief on the same topic. Because their subject matter matches, their vectors point in the exact same semantic direction. But because the long brief repeats vocabulary terms, its raw values expand outward, creating a massive spatial distance between them. To eliminate length bias, data scientists discard Euclidean distance entirely and look exclusively at the angle between vectors. This metric is known as cosine similarity. By dividing the dot product of the vectors by the multiplication of their absolute magnitudes, we effectively shrink both lines down onto a normalized unit arc. If the angle between vector coordinates is 0, their cosine score returns a perfect value of 1. This mathematical correction guarantees that your NLP models categorize, search, and cluster documents strictly based on semantic conceptual truth, completely independent of how wordy the author chose to be. The final hurdle when building a document term matrix is handling the sheer scale of human vocabulary. If your algorithm analyzes millions of text documents, it won't just discover standard words. It will ingest misspellings, email signatures, hyperlinks, and jargon, bloating your matrix's vocabulary columns to an unmanageable scale. If your dictionary contains 1 million unique tokens, every single text vector you store will be 1 million dimensions wide. This vocabulary explosion results in severe data sparsity and causes local computer systems to rapidly exhaust system memory. To protect against this bottleneck, production-grade NLP systems deploy a data engineering trick known as feature hashing. Instead of allocating an explicit, hard-coded matrix column for every unique word, a mathematical hashing function intercept is introduced. When a token like liability or patent streams into the pipeline, the hash function processes the string characters and converts them directly into fixed range numeric indices on a highly compressed array. This deterministic compression bounds your feature matrix to a fixed, optimized memory footprint, keeping calculations lightning fast regardless of how messy your raw text collection grows. Up until now, we have assumed that our document database is static and perfectly clean. But in production software development, raw user data is unpredictable. What happens if a user searches for a newly coined tech term, or a word containing a bizarre typo that never appeared anywhere in your original training corpus? Let's look back at our inverse document frequency formula. If a token does not exist in our training database, the denominator drops cleanly to 0. Mathematically, dividing our total document count, n, by 0 causes an immediate explosion to infinity, crashing your production machine learning pipeline. To bulletproof our engine against this zero division bug, engineers implement 2 structural defenses: Laplace smoothing and out-of-vocabulary fallback slots. Watch how the math transforms to handle these edge cases. By injecting a constant value of +1 directly into the denominator, we guarantee it can never drop to 0. We also add a +1 outside the log function to ensure that rare words don't completely vanish from the vector map. With these smoothing adjustments, a completely unknown word safely resolves to an explicit, predictable score. This mathematical defense ensures that your feature matrices remain structurally sound, stable, and ready for deployment in unpredictable real-world applications. Where do engineers actually deploy this vector map in production systems? While modern deep learning handles complex nuances, TF-IDF remains an essential industry benchmark due to its blistering speed and clear interpretability. Its most famous application is information retrieval in search engines. When you type a query, The search engine doesn't just look for exact word matches. It scores how distinct your query terms are inside its indexed pages using TF-IDF vectors, ranking the most informative pages first. It's also the backbone of automated document classification and clustering. By evaluating the vector distances between row profiles in our matrix, algorithms can instantly sort millions of unlabeled emails, news articles, or customer feedback logs into clean, thematic buckets without human intervention. From serving as a baseline feature extractor for text classifiers to running lightweight, high-speed keyword profiling tools on the edge, TF-IDF bridges the gap between human language patterns and hard vector geometry.